Good morning. Geography 141, Chapter 3. This is going to be a totally quick rush. This is a really dense chapter. 3 and 4 are wild, so hang on. So the book starts out talking about the difference between shortwave radiation, that's radiation that's coming from the sun, and long-wave radiation, and that's the radiation that creates the heat. So check out that diagram and look at the different pathways that shortwave radiation follows. So it can come in, it can be reflected by the clouds in the atmosphere and never get to the Earth, which is a good thing. Because if all of the shortwave radiation got to the Earth's surface, the surface of the Earth would be ridiculously hot. That goes into this concept of albedo, and that's the reflectability of different surfaces. So it's the portion of light that gets reflected. I want you to be able to talk about the different pathways, the different albedo percentages on the Earth's surface. Talks about fresh snow reflecting more. Green grass has less albedo, and people who have done a lot of skiing know this, that if you're out on a fresh snow patch, you can get sunburned more easily than on a just sunny day walking in a green field. So here's some of the albedo rates to be aware of. The text also talks about refraction, so that is shortwave radiation passes in through the atmosphere and hits moisture, atmospheric particles. Those different wavelengths of energy separate into the color spectrum, and that's why we perceive rainbows. Talks about mirages, those heat wave surfaces that you see sometimes on the road are light refracted. It also talks about this extra 8 minutes of daylight that we get as the sun has actually set, but what we're seeing is the reflection or the refraction of sunlight 4 minutes after sunset and before the sun actually rises. We don't actually see the sun, we just see a refraction. Book talks a lot about clouds and how variable clouds are, and that's one of the things that makes climate modeling and climate prediction so difficult, because clouds can reflect shortwave incoming radiation, so that shortwave radiation never hits the Earth's surface in order to turn into long-wave heat radiation, or it can be trapped. Down here is an example of long-wave heat radiation being trapped by, here it is, trapped by the cloud layer and kind of being held in. Book talks about this lag time in radiation. So why, if maximum solar radiation, we can look at this diagram, maximum incoming solar radiation is at noon, but the maximum temperature happens later, and that's because the incoming radiation has to be converted to long-wave heat radiation, and that takes a little time to happen. So sometimes noon you're more apt to get more exposure to the sun, but you're going to feel the heat effects later in the day. And then the old greenhouse effect, and this is how shortwave and long-wave radiation work to keep a greenhouse functioning. So shortwave radiation can penetrate through the glass surface of a greenhouse. When it hits the surface inside the greenhouse, it gets converted to long-wave or heat radiation. And that's the same concept then when we talk about the effect of greenhouse gases. That shortwave radiation gets allowed in, but there's so much particulate matter, so many greenhouse gases that long-wave heat radiation then gets trapped. The book talks a lot about an energy budget, how much comes directly to the surface, how much is scattered, what is the overall albedo or reflectivity of the Earth's surface, the total amount, and then what we end up with, though, is a surplus of heat at the equator, and how this is really an important aspect for generating atmospheric and oceanic circulation. I don't know if this is in your book, but it's a nice little cartoon or diagram to look at the different pathways with shortwave radiation and long wave. If you think about shortwave, really it's just kind of being light energy, and it doesn't really get that heat aspect until it interacts with the Earth's surface. The book then moves into these ideas of heat transfer, and three methods that the book talks about: conduction, convection, and advection. And conduction is that molecule to molecule transfer. If you put your hand directly on a burner, the bottom of your hand is going to get hotter before the top of your hand gets hotter. They use a pan, which is probably a safer example. So if you put a pan on a stove top, the bottom of the pan and the water directly above the bottom of the pan is going to heat, and so that is a small direct impact. Convection is once those molecules begin to warm up, they rise, they expand, and that causes this vertical motion and this mixing. So the bottom layer of the liquid in the pan is hot, it begins to rise. As it rises, the colder water flows down to the bottom and it gets hot, and it begins to create this circular pattern. Now, advection happens once in an atmospheric heating. Once those parcels of air heat up at the Earth's surface and begin to rise due to convection, then wind patterns can begin to take those warm parcels of air and move them horizontally. So when you look at just a general global temperature patterns, what you see are a pretty striking high temperature pattern along the equator. Much cooler temperature, that's the purple and blue, as you get to the poles. And when you get over these land masses, so this is a large European landmass, you get very cold cells, and over North America you also get very cold temperatures. So what's causing that? Well, when we look at temperature controls worldwide, the first thing you want to remember is that latitude is the primary actor here. So if I look at this, you could generally say temperature gets colder as you move up in latitude or down in latitude from the equator. The second temperature control is altitude. So higher land masses, so mountain areas, are going to have cooler temperatures than lower land masses. The third control would be cloud cover, and we already talked about how variable that is. It can either keep it warmer, so it's like having a blanket at night where it keeps that warm air in, or it can be much colder. And then the fourth control on temperature is land-water heating differences. So let's look again at latitude. Even when we look at seasonal differences, so January versus July, you still have a general latitudinal control. You can see July, that warm band has shifted north a little bit. In January, the warm band has shifted south. But all in all, it gets colder as I move up toward the North Pole, colder as I move down toward the South Pole. Cloud cover, what affects or impacts cloud cover is height. At any given point, 50% of a landmass can be covered by clouds, and it works in two ways. It can keep, during the day, it can keep shortwave radiation from coming in and warming up the Earth's surface. But if you get a cloud bank at the end of a day, it can also keep the warm energy in. Altitude is the third temperature control, and remember in chapter 2 we talked about this little diagram that as you move higher in altitude, the air pressure is less, and if the air pressure is less, there are less molecules. So the density changes as you go higher in altitude. There's less molecules to hold the heat. All right. We're going to move down. And the fourth control is called continentality, or the differences between land and water heating. And this diagram, I think, is in your textbook. And what you see is that land surfaces heat up much faster than water bodies. And the reason, one of the reasons is that there's no mixing. In water, you've got the warm air or the warm molecules beginning to create a circulation, so warm water and cold water are mixing, and eventually the water will heat up, but it takes much longer than trying to heat up the surface of the ground or the surface of the rock. So land masses cool down much more quickly, they heat up much more quickly, and large bodies of water tend to be a reservoir. So here's a great exam question. When you look at Oregon and New York State, both of them are at about the same latitude, and we said first off latitude is a major contributor in temperature. So why is this an exception? Why is Western Oregon generally warmer than the state of New York? So this chapter really talks about all of the pieces that take shortwave radiation, convert it to long-wave radiation, and how the Earth's surface heats up. One of the things I could ask on an exam is to explain why this air mass over Asia is much cooler than the air mass over North America. And then here's another exam question. I could ask you for these four cities or these four places, Oregon, the spot in Russia, spot in Saudi Arabia, and the spot in Switzerland, what is the major influence in the temperature for these areas? Some of it is going to be continentality, some of it's going to be latitude, some altitude. So kind of take all of these things in this chapter and think about how those all contribute to create these different climate and weather patterns.